here's an example of using the big kinematics equation. Let's look back at that thrown chalk. Before we talked about I threw down the chalk at 2 meters per second. How fast did it go after a half second? Now the question is, how far did it go in a half second? We could ask that question as well. So let's think about the experiment. Well, first I need to do it, but we're on a limited budget. Let me get a short piece of chalk here. So we're going to throw it down at 2 meters per second. How far does it go in half second? So always draw it, right? So here's the chalk. Throw it down, start at the origin. It's going to have an initial VI of 2 meters per second, initial velocity. And it's going to start at the origin and go down. And that's positive because, as always, well, not always, but in most of these lectures for the moment, positive x is down. Start at the origin. That's what we're describing. So really, you just describe that equation. xf is xi plus vit t plus 1/2 a t squared. Right? So let's just plug in, see what we get. The initial position is 0. I'm assuming I released it right at the origin. Right? So 0. The initial velocity is 2 meters per second. And the time we're talking about is a half second, so 2 times 0.5. So the initial velocity is going to make it go a meter. But then it's also accelerating down at 9.8 and then 0.5 seconds squared. So you just plug in your numbers, right? This is about 1. This is about 1/8 of 10, which is about 1.25. So you add these together, and sure enough, the exact number is 2.225 meters. So the only tricky thing here is you got to think about, you get all these signs right. Right here, everything was positive because everything was down. What if we did the opposite? What if we throw it up at 2 meters per second? That sounds a little bad, but let's just go with it. We throw it up at 2 meters per second, meaning I'm so happy with the class. Oh, look at that. It goes up. How would this be different? xv, let's see, x final would be the same equation. Initial is still 0 meters per second, plus, but now vi is negative, right? Because I threw it up, down is positive. So it'd be -2. -2 times t is 0.5, right? And then the acceleration is still down. Gravity is always down. So plus 1/2, 9.8, 0.5 squared. And you put all that together, and I get 0.225 meters. Right, so different because now it has threw it the other way. Right? Oh, let's see. We have a question here about this plug and chug problem. Let's see, what are we concerned about here? And it looks like Trenton Boy, shouldn't the final position have been negative, up? Let's see if we can figure out what Trenton Boy is talking about. Shouldn't the final position, I think we did it right. I think, oh yes. So Trenton Boy, that's good. He's using his intuition. Boy, I'll assume it's male. I think that's what boy means. Threw it up, was expecting the displacement to be up. And that's a good guess. And actually the way I threw it, after half a second, it probably still was up. And up would be a negative number. But the way the numbers worked out, it actually turns out that the acceleration was strong enough that in half a second it had turned it back down, and it was actually lower. You can actually tell because this is bringing it down by a meter. Or I'm sorry, this would have been pushing it up by a meter, but this is bringing it down by 1.25 meters, or 1.225 meters farther down. So in the end, the acceleration tugged harder. So let me give you a more realistic look. There you go. After a half second, it had made it into the positive, the further down territory. So we did do it right. We now derive 2 equations of constant acceleration kinematics, but some problems kind of need a different one. What if you accelerate over a displacement delta x rather than a time t? Now really, you accelerate over both. You accelerate for some distance and some time. But sometimes a problem, rather than giving you the time you accelerate, might give you the distance you would accelerate. So what do you do then? Well, really, you can use the same equations that we've been using. xf, the final position equals the initial position plus the initial velocity times time plus 1/2 a t squared, and the final velocity equals the initial velocity plus the acceleration times time. That's really the only two equations. If you wanted to solve that problem, you would have to use both of them. But it turns out you can substitute them together in a way that simplifies into something so nice and simple and concise that we tend to memorize it as a third kinematics equation. So let's go ahead and combine them and see what happens. Let's see, let's combine to remove the time t. Okay, so what we're going to do is solve this for delta x. Let's see, so we'll go back to writing it as the displacement. And then we have here vi times t. And then t, though, we're going to solve this for t and just plug it in, and that'll get rid of the t's. We're going to solve this for t and plug it in here and here. So that's going to be vf minus vi over a times vf minus vi over a. That goes there. I'm going to ditch the vectors because this is going to get a little weird. It's going to get weird. And let's see, so that solves that t, and then plus 1/2 a. And now we need that same t squared, vf minus vi over a squared. All right, very nice. Let's see. So what we're going to do is multiply through the whole equation by 2a. Why not? One reason is I know what I'm heading for here. 2a delta x is part of the thing we're looking for, but that'll also cancel some nice stuff out here. So a 2a here, the a will cancel that a. You'll end up with 2vi times vf minus vi. All right. And then plus, and the 2 will cancel that 1/2. You'll have another a. That's a squared, and that is a squared. So that all cancels. So you just end up with vf minus vi squared, like that. And then from here, there's a few ways you can do it. Some people like to, I forget what some people like to do. Let me just show you what I like to do. Here's what I like to do. I like to then say this is 2vi vf minus 2vi squared. I like to do it the hard way. There's easier ways to do it. I forget the easy way, though. Plus, what is the easy way? I don't know. Plus vf squared minus 2vf vi plus vi squared. I really should do these ahead of time. 2a delta x. Oh, what have we done? What have we done? We have 2vi vf here, and we have negative 2vi vf there. Whew. And we have minus 2vi squared here and vi squared there. So you combine those, and that's just minus vi squared, right? So you could then say vf squared, if you want to solve this for vf squared, equals, we'll bring the remaining vi squared to the other side, plus 2a delta x. And that is the form that a lot of people use and memorize these equations when you have an acceleration for a certain time. And you want to think about the velocities. Final velocity squared is initial velocity squared plus 2a delta x. Or you may have heard it called just 2ad, the distance over which you apply the acceleration. So we could use this for a quick, the whole throw the chalk thing. What if we threw it for a meter? Right. Throw for 1 meter. What are we going to get? How fast will it be going? Vf squared is the vi squared. We threw it down at 2 squared is 4. Now 2, the same problem we keep doing. Vf squared plus 2 times 9.8. And then the d, say we threw it and went a meter. D like that. That'd be 4 plus 20, 24. Take the square root, and I didn't finish the problem. I apologize. Let's see. 4 plus 9.8 times 2, 8 is 16, 18, 19.6 plus 4, like the square root of 23.6. It happens sometimes. I'm trying to give you the real classroom experience. I just didn't want you to think that this is some fundamentally new kinematics equation. It really isn't. It's a combination of these two equations. We've covered the basic equations of 1D kinematics, and now we're going to show you how to solve a few of the tricky problems. There's the straightforward problems where you just plug into the formula. There's always a few that are sort of a little bit more conceptual. You have to really understand the equations to solve them. So the first kind I'm going to show you is called, I call it a two-body problem. Let's not just keep up with one object in one-dimensional kinematics. Let's keep up with two objects and keep up with maybe their relative position or something like that. That really makes you use the equations in a way that you understand them. I call this one the meeting of the band nerds. If this offends you, you could call it the meeting of the marchers if you're sensitive or you have sensitive students. So to do the meeting of the band nerds problem, you also have to understand American football. Okay, so this is the end zone. I have a deep understanding of American football. The end zone is over here, and the end zone is over here. And you know that the football field's 100 yards along, and in the middle is the 50-yard line. And we're going to imagine we got a marcher over here, band nerd over here, and this one is just playing a piccolo. So it is moving at VF, we'll call it V fast, of 5 feet per second. Yes, I am not using MKS for once here. And over here we got a marcher that is playing what's that big sousaphone thing that like wraps around their body, you know, like that. So they're carrying that big heavy thing. So they're only moving that direction at V slow of 1 foot per second. And the question is, where do they meet? So that's a question that you can solve with simple one-dimensional kinematics, but there's no formula that you can just plug in. It's not a single equation that you can use. You have to use a few equations. So the way to solve these sort of two-body problems is write the equation for each body, and then think about what you need to make equal. All right, so first let's write, for each one, let's just track their position. This is just one-dimensional and it's constant velocity kinematics, nothing speeding up. So the one you want is that the x final, or the position of the fast person equals their fi, the fast person's initial position, plus their velocity of the fast person times time. And then the slow person, x slow equals x slow I, wherever they started, plus their velocity times time. All right? We could go ahead and put in numbers. If we consider this the origin for now, even though a football field is kind of strange, if this is the origin, then the fast person has no initial position. They're at 0, and they're going at 5t if we're working in feet and seconds. And slow person, they begin at an initial position of 100 yards, which is 300 feet. So their initial is 300, and then their velocity is actually backwards, right? So if these are vectors in 1D, the VS would be the vector component, but it is negative because it's this way. So minus, and it's 1. It's kind of awkward. I'll write a 1, and then times time. So there's the two equations that describe their motion, 5t and 300 minus t. So when you want two things to meet, you got to think about what's going to happen. When they meet, they're going to have the same position at a certain time. So the sort of way I would probably start this problem is to say, find the time, I'll call it t star, when they meet. And you got to figure out what is the mathematical requirement that they meet. It's that they're at the same position, all right? It's that xf equals xs, all right? So when they meet, the fast person's position will equal the slow person's position. So we can say that's going to happen when 5t equals 300 minus t. And now, something very important. When I write something like this, I like to put a star, okay? Because this is no longer a variable t. This is now a specific time. It's the time when this happens. So this equals this at t star, and here's how you solve for t star. All right? So let's see, this would come over here and make 6t star and go into there, and you get that t star is 50 seconds. It takes 50 seconds for them to cross the field and meet. That wasn't the question. It wasn't how long till they meet. It was where do they meet. So now you just take that 50 seconds and plug it back in. So if you wanted this one's position, x final, it would be 50 seconds times 5, it would be 250 feet. And if you want to check your work, and I always recommend you check your work, then you could also check x slow, not final, I'm sorry, the fast, x fast. The slow person's position would be 300 minus 1 times 50, 300 minus 50, 250. Look at that. So sure enough, they are in the same place, 250. But was that the question? If you're in America and you're watching some football, you don't say that they met at the 250-foot line. No, that's not what you say. They're at 250 feet, so that means it's 300, they're about right here from this end zone. So you divide your 50 feet by 3 to get yards, and you get that they're on, technically, they are on the 16.667 yard line, but if you're in America, you don't say that either. They're on the 17-yard line. About a football past the 17-yard line. So that's how you do two-body problems. They get even more complicated because sometimes the story is more complicated. Here, I just had nice little uniform motion, constant velocity. You might have also had one accelerating because they were so excited to meet the other person. Or you might be given up to a certain time they were accelerating and then they went at their constant velocities. There's lots of ways to complicate it, but the basic idea is this, is figure out when did they meet.